and was friends delivered a lecture about, you wouldn't believe, golden ratio. And today, as I understand the situation, we shall have a lecture about how to regulate splicing, essentially.
How to repair mutations using SPLICE switching.
Okay. So we have our guest, Professor Luis Garcia from the University of the South, and he will introduce himself. Okay. Thank you for coming.
No, I thank you very much for this invitation. So I am Luis Garcia, and I am Director of Research at the CNRS. CNRS is a National Center for Research in France. Like that?
Or if you can go work with this. Yes.
Does it work? Yeah. And I am the head of INSERM laboratory here at the University of Versailles. This is a Faculty of Medicine at Versailles Saint-Quentin. And we work very closely with two associations, two charities. Duchenne Parent Project France, patient organization, and the Association Monégasque contre les myopathies, the equivalent in Monaco. So Monaco is kind of France, and it's not really independent. And with these two charities, and also the university and INSERM, we have also founded two companies, private companies, that are headed and owned by these charities, so by the patients themselves, which are one in Switzerland, in Bern, Sintena, and the second one in Versailles, in the same building, and connected with our academic research, which is SKY Therapeutics. SKY because Saint-Quentin-en-Yvelines, which is the name of the agglomeration. And we have been working with these guys now for 20 years and 15 years on SPLICE switching using TcDNA. And we started from ground zero. At the very beginning, we started with gene therapy and the U7 system. It worked very well, but it has some problems. It's gene therapy with regulatory problems. It's difficult to produce at GMP levels. And then we shifted, or we did in parallel, an alternative using antisense oligonucleotides, using analogs of DNA to produce the small sequence that should interfere with the messenger. I'll show you after how it works. It was very long because we started from ground zero. These TcDNAs are very difficult to produce because they are not natural. They are not commercially available. You cannot buy them on a catalog and build your 15 or 20 mer, meaning sequence of 15 or 20 nucleotides with a machine. You can do it fast. In one night, you have the compound ready for use. But to make the TcDNA blocks, there are 23 steps, meaning that if each step is about 90% efficacy, you can start with all the universe, the matter of the universe, you have nothing at the end, because there are 23 steps. So it was very long to set up the conditions to produce these compounds at an industrial level in order to run clinical trials and to propose an alternative to patients. So now let's go to our concern. So we are a laboratory that work on fundamental myology, basic research on myology, on muscle development, and also on therapeutic avenues. So we have been working on stem cells, on growth factors, gene therapy, of course, many types of gene therapy, and oligos. And nowadays, what seems to work very well is splice switching approaches, and we can apply, and we are applying actually, for Duchenne muscular dystrophy, a very severe, and I will show you after what it is, muscle disease, Pompe disease, another muscle disease, spinal SMA, spinal muscular atrophy. You know that there is a compound which is cell. There are actually two compounds, one for gene therapy, one for oligos. Gene therapy is $2 million single injection, and with oligos is $500,000 per year for life. So they are very expensive, and our goal is to shortcut this cost in order to make them available for everyone. I mean, we need. Epidermolysis bullosa, we have a collaboration with a British charity, um, and it seems to work, and we plan a trial after Duchenne on that disease, and DM1, another muscular dystrophy. So for all these diseases, we can use the same kind of oligos, the same strategy, systemic delivery, and of course, the oligo is designed as a sequence which is specific for each of these diseases. But the bottlenecks are the same, because finding the sequence, I don't say is a piece of cake, but it's very doable, and you have just to analyze the target and find the best target. I mean, the best key for to unlock the exon. But there is a common problem, which is toxicity, delivery, and lasting effect. Let's go now to Duchenne. So Duchenne is our first concern. It's a devastating condition. It was described first, as you see, in the middle of the 19th century, and so far there is no cure or something satisfactory, at least. There have been many trials because it's quite emblematic. It is emblematic myopathy. It affects one boy out of 3,000 at birth, which is quite a lot, finally. If you look at stadium, for example, stadium, there is always men, boys. And when there is 30,000 people, you have just to count that there is a couple of buses full of patients with in wheelchair. The symptoms are obvious at 3 of age, meaning that for families they may have several boys with the same, because 50% of these cases are transmitted by the mother, it's X-linked, and 50% are de novo cases. So when the de novo, usually there is only one boy affected. But for the familial cases, because of the familial planning, sometimes families have 3 boys in 2 years or 3 years, and the 3 could be affected if the mother is a carrier. So it's really it's very critical. It's a progressive disease, so by the age of 10, boys are usually in wheelchair, and they have respiratory insufficiency, cardiac anomalies. And until when I started research on the disease, meaning in the mid-80s, the boys die before being adults. It was a pediatric disease. Nowadays, with the care that improved, there is not yet a cure, but care has improved a lot. Small things, but many small things can change also the course of the disease. Now, there are still boys that die before 18 or around 20, in their early 20s, but now there are patients of about 40 years old. They are in bad shape, but they are still alive. And this was not possible 20 years ago, which means that many things have changed, and because they are not asking the same. 20 years ago, it was the parents that were fighting against the disease to save the kid. Now the kids are adults, and so they want to something else. They are not kids. They are other needs. They are needs of man, and so this is why we are trying to combine different strategies, restore the gene as soon as possible, and for those who are already in wheelchair, improve their quality of life, and maybe with using robotics or stem cells, rebuild what is already missing now, which is not cannot be repaired only by splice switching. So it's a complicated disease because it's a progressive evolutive disease. So the battlefield change every year, not every year, but every 5 or 6 years, the battlefield is different, so the solution is different. The solution that we propose before, when boys are ambulant, are completely different, or will be completely different for boy of 30 or 25. And there are also some cognitive deficiency that can be associated, but it's not always. It's very few. So what is the gene? That gene is very peculiar. It's DMD, the DMD gene. The DMD gene was characterized by Luke Kunkel in the mid-80s, and it was found first in man and then after in mouse. It was the first time that it was on the contrary. So we had a model for that disease, and we didn't know that we had it because the mouse feels completely different without dystrophin. In man, dystrophin, the lack of dystrophin is, I would say, very severe phenotype. It's not severe in mouse, and it's very severe in man. It is the largest largest gene ever sequenced. It's about 2 million base pairs. It means that 2 million base pairs means 2 centimorgan. 2 centimorgan means that you can see it under the microscope. So it's a very expensive gene. And so it should have roles that we don't know yet, even at the level, at the genetic level, at the structural level of the chromosome. Because 2 million nucleotides has to be transcribed into a pre-messenger, which is very expensive. It takes 18 hours to transcribe. And you see here the exons, so the small part of the messengers that will encode the protein, and here the introns. It was called junk DNA or RNA, whatever, until very recently. We know now that it's very important. It's important because there are information there, and some have been identified for other genes. Here we don't know, but this should have a role. So the messenger here would be spliced. I mean, this messenger will be spliced into an RNA messenger containing 79 exons. And you see here the size, 40 kilonucleotides, 40,000 nucleotides for the full-length messenger, and 2 million, almost 2 million nucleotides for the pre-messenger. So it's large cost, a large garbage. That's different promoters because there is a protein that is expressed not only in muscle but also in cardiac and brain and retina. But the most important is in the muscle and heart. So the full length is a 36 about 3,600 amino acids. It's 427 kilodalton. It's quite big. It is located just beneath the sarcolemma, the membrane of muscle. You know that muscle is not a cell, skeletal muscle. It's a syncytium, meaning that it's cells that have fused to give a tube with different nuclei. So the protein is located just beneath the membrane, the sarcolemma, called the sarcolemma. It associates a large complex of protein, which have been discovered in the 90s, and there's always a new protein that is found to be linked more or less close of the dystrophin. And when this protein is absent, when dystrophin is absent here, all these complexes disappear, or is not properly aggregated, and many functions are not running correctly. And you see that there are adhesion molecules. So here you have the basal lamina, extracellular matrix, and here's the cytoskeleton. It's kind of linked in between these two structures that aggregate many things. And here you have in immunostaining, so the nuclei are in red. This is a section, transverse section of a muscle. And in green, you see the dystrophin around the muscle fibers, like tubes, like a sausage, are all parallel. And so dystrophin is around, and when there is no dystrophin, of course, the picture is black, and the muscle degenerate. Because this time the muscle contracts without dystrophin. In absence of dystrophin, the fiber is more fragile, and it breaks, and then it regenerates. So it regenerates for a while, but not forever. And there is an impoverishment of stem cells, muscle stem cells, and also other mechanisms, likely due to the neuromuscular junction. And at the end of the day, the muscle turns into fat and into fibrotic tissue. What are the type of mutation? Because there are many types of mutation. There are large mutation, and this is a gene which is very large. So there are pieces of the gene that are missing. And there are deletion concerning one or several exons. And deletions with half a million nucleotides, half a centimorgan, are quite usual in that gene. That duplication, very few, nonsense mutation, many times. And what is very important, because there were two diseases discovered in the 19th century, Duchenne muscular dystrophy and Becker muscular dystrophy was the name of the two physicians that discovered, that characterized the disease. And with the rise of genetics, it was found that these two diseases were on the same gene, DMD. And the very difference was that patients with mutations, more often deletions, that affected the reading frame of the messenger. You see the messenger, 79 exons, and the frame is painted in colors. So you know what is a frame. You know the RNA is translated into amino acids with 3 codons, three nucleotides. And the color says that if there is 2, 1, 3, 3, or 1, 2. So if an exon is missing, or a couple of exons, for example, like here, in a patient with severe phenotype, this is classically a DMD. This patient missed exon 48, 49, and 50. Exon 47 and 51 are not in frame. The colors do not match. So there is here a premature stop codon, and the protein is incomplete and unstable and disappear. So this is a very severe form. In the case of BMD, Baker, so these guys have almost the same deletion, but the deletion is even bigger. And the exon 51 is also gone. But this time, 47 and 52 are in frame. Meaning that, of course, the messenger, something is missing in the messenger, but fortunately, because there are these repeats here in the middle of, here in the middle you have these repeats, 24 repeats, and some of them can be removed without losing too much of the activity. And the protein is fairly stable. So we consider that it's semi-functional. Sometimes it is fully functional. And actually, we have identified 2 guys, adults. They were semi-professional. One was soccer player. Another one was a rower. And they were catch because of anti-doping testing. The creatine kinase was a bit elevated, and then they passed automatically through the scan of muscle dystrophies, and we found that they were patient Baker, but they were quite good guys. Another one is a family. So it was a family. The mother was a carrier. They got a boy with Duchenne. The mutation was known, and they had a daughter. And the question when the daughter grew was, is she carrier or not? Because it's X-linked. So the physician took blood from the mother, from the boy, he has a mutation, from the girl to know if he had a mutation, and the father was in the room. He said, we take a control, positive control, normal control. The father looks normal. They ran the genetic analysis, and they found that the mother was a carrier. Of course, they knew that. The boy had a mutation, clear cut, he is homozygote, since he is XY. The girl was carrier, normal allele and mutated X, but it was not the X of the mother, which usually we can doubt on the paternity, but the maternity is more difficult. And fortunately, the father was also in the analysis, and indeed, the father had a mutation on the DMD gene, and the mutation was delta 5152. You see that 50 and 53 matched together, yellow, yellow. So he was a Baker, but asymptomatic Baker. So this tells us something about the rationale. It means that if we can remove exon 51 in this patient with kind of pattern of deletion, 48, 15, and there are half a dozen of possible patterns that could be rescued by skipping 51, we could change the fate of this patient by moving them from DMD world or universe to the BMD universe, to a boy who has a shortened life, to someone that can work until his 70s or 80s, eventually be asymptomatic. The truncated mRNA. So the goal is to remove that. It was a kind of science fiction 20 years ago, but now, I mean, it's quite efficient. We have tools, easy tools with antisense that can do the job by masking during the messenger. So the goal is not to modify the genome of this patient. The goal is to modify the RNA messenger for dystrophin as soon as it is produced during the maturation in order to correct it at the level of the first product of the gene. So the gene is always disabled, but the product is restored. The other advantage, and I will say a word at the very end, is that, and this is the difference with gene therapy. Gene therapy, there have been some attempts to introduce a normal gene, because you say, would it be better to have a full-length dystrophin or this kind of truncated guys? Of course, full length would be better. Fully functional, semi-functional. Fully is better than semi. The point is that these patients have never seen normal dystrophin. So the dystrophin would be rejected. Maybe not the first week, maybe not the first month, but after a few years, after an episode of vaccination or whatever, fever, whatever, the full-length dystrophin could be. It's a Damocles sword, you have on the head. So it's better to have that kind of protein because these patients, because splicing is not perfect. Nobody is perfect, and splicing is not perfect. Splicing does a job, but sometimes don't splice the right correctly. Meaning that these boys, if you look carefully, have some truncated exon-skipped proteins. They have some. We call them revertant fibers. We don't know the mechanism, the very mechanism of this reversion, but it's by skipping some exons, one or several exons. So there is a library of skippings, possible skippings, from the very beginning of the life that makes that protein belongs to the self, even in that patient. He has very few. In the mouse, we can find all of them because we can kill a mouse and chop mouse. A human being is just a biopsy, a small biopsy. There are ethics now, and of course, in deontology also. So if we are lucky, we can find one or a few. Sometimes there is not, but it doesn't mean that in the opposite side there is not very few. So this is the rationale. Turn BMD into Baker. So how do we do that? And I'm talking now for the younger, for the young people, for the master and undergraduate. So this is just two movies, two very fast movies, videos, didactic videos, showing what is splicing. Splicing, here you have two exons and one intron. It's a kind of watch mechanism. It's very complicated. It involves many proteins, dozens of proteins, and SNRNPs. SNRNPs is a mix of small RNAs mixed with proteins, and it's complicated. And every exon has a peculiar machinery, and it gives a splice. Exon skipping means interfering with that machinery. And interfering means just putting something, a stone, in an engine. You will stop it. Sometimes it works, sometimes it doesn't. So you have just to find what type of interference you need for that specific exon. So we have not a single, I would say, approach, but maybe different approaches, different ways to attack one exon, but it's always with something, an antisense that will stick the RNA by Watson-Crick interactions, and then stay blocked and either unfold or mask a site which is required for a protein to sit on the messenger, or unfold the exon, meaning that the cathedral fall down, etc. And at the end of the day, you can skip an exon. I told you before that we can do that by gene therapy, but here I will just show you how difficult it is and why it takes so long time to develop that kind of compound for human purpose. So a few years ago, we started a collaboration with Christian Leumann. Christian Leumann is a bright chemist at the University of Bern. Now, actually, he's a rector of the University of Bern. And he developed a new kind of DNA analogs, Tricyclo-DNA. Here you see the 3 cycles. Here, 1, 2, 3. You recognize, I would say, the DNA backbone, and here are the 3 additional carbons. So to add these 3 additional carbons in the building block, it's 23 steps. So it's very complicated. And they have some interesting properties, such as the inability to elicit RNA activity, which could be interesting for knockout, but in our case, we don't want to destroy the RNA, we want to modify the RNA. It has an increased stability, so it's very stable. Increased affinity, RNA affinity, so it's very sticky, and it's also hydrophobic. I think this is more theoretical than real, but it is more hydrophobic. I don't think it plays a role in our case. And we have published that the efficacy of this kind of molecule 4 years ago in Nature Medicine, and you may find this paper by just typing Goyen et al. And in that paper, we compare our chemistry, our Tricyclo-DNA, to the 2 chemistries that were at that time used for clinical trials. One by Preclinical GSK, the 2' methyl phosphorothioate in green here, and the morpholinos or PMO by at that time AVI, which is now Sarepta, in orange. And here you have the activities at the level of skipping. So we use here the mouse, the MDX mouse. It's a surrogate. Here's the mutation lies in exon 23. And it's different from human situation. It's a peculiar singular mutation, but fortunately, exon 23 can be removed, and 22 and 23 are in frame. So we're the same rationale. So here you see the levels of skipping at low dose. We called at that time low dose 50 mg per kg, which is already quite high, but we call it low dose, equimolar dose, and high dose 200 mg per kg. And you see in blue the tcDNA, so in green the 2' omecyl from GSK Prosensa and the morpholino. And whatever the concentration, whatever tissue, here you have the different tissues, different muscles, tibialis anterior, this one, the gastrocnemius, this one, the quadriceps, the triceps, biceps, diaphragm, and heart. Heart is very important. Diaphragm too. Diaphragm is for respiratory function. Heart is a cardiac muscle. So I told before that these boys die because of heart failure, cardiac failure. So it's very important. The other compounds that were tested in clinical trials do not target what is really needed. I mean, the vital function. So we were very happy. This was why we were quite successful in entering in Nature Medicine with a mouse study when there were already human trials. Actually, the 2' omecyl failed, and the morpholino failed also, but the FDA approved the compound for marketing 3 years ago to save Sarepta as a company against the advices of the commission. I mean, the scientific medical commission said that there is no effect at all. I mean, it was an increase of 10-fold in skipping, meaning that it goes from 0.1 to 0.9 after 2 years of treatment. So it's 10-fold sounds very important, but 10-fold zero is still zero. So, but the American, it was just at the moment when Trump was elected, it was in between the elections. And to save the company, they say, you can sell it, approved. It was approved at $500,000 per year, the treatment, for something that is useless. So, it's just crazy. It's only money. So here it's, again, for the comparison in that paper, here we show the presence of the protein, because skipping is fine, but skipping without protein is meaningless. So here you have the normal protein, normal level, and here the levels that we rescue after skipping, after 3 months of treatment at different dosage, high dose here and equimolar here. So you see that at high dose, levels are almost normal, not undiluted here. While for the others, and this one, morpholino, which was approved, it was really ridiculous, the level of protein. But well, life is never easy, so we were very happy at that time. We say, okay, it works in mouse, even if the dose is high. It seemed at that time very safe, because nobody was hurted with that. All mice were survived, cardiac function was improved, respiratory was improved, ambulation was improved, everything was improved. So we said, we move to human. So we developed an antisense for exon 51. And then it was drawback, catastrophe, anticlimax. Mice die at the time of injection. We had never seen that before. And it was a kind of anaphylactic shock. So it blocked the project for a couple of years. And back to the trees, we had to find the reason of the toxicity and to detoxify. And what we found is that, actually this work was done by Fedor, he's here, Fedor Sunachuk. So he analyzed the proteins that bind this compound, this Tricyclo-DNA, either from the serum, because it was a shock when injected into the bloodstream, from human or from mouse, and with the compound either with phosphodiester internucleotide linkage, the natural linkage between DNA, or with sulfur, which should improve the biodistribution. With sulfur, it improves the efficacy. But apparently, it has a problem, because the PO are never toxic, while the same with PS can be toxic. They were not in the case of MDX, but they were in that case. And you see here the protein that are bound by this compound just by putting into all the proteome. All the proteins from the blood are fixed by the sulfur in a non-specific way. Meaning that here you have protein from the complement activation, from the coagulation, from everything. So you destabilize everything. And more importantly, why some oligos were toxic and others were not. We thought that maybe there were some sequences, specific sequences that were toxic. So we did a lot of speculations and experiments, and we had we found a lot of explanations. All were wrong. At the end of the day, we found that these oligos that are not supposed to match each other, homodimerization, did some. They did some. They could do depending on the sequence. Only because these oligos are so sticky that regular DNA or regular RNA is single-stranded, but here with very few, tricyclo can stick and it's very stable. And when these homodimers or homodimer-like are formed in the presence of sulfur, it can kill the animal. So it was very important when we designed the oligos to consider that and to just remove all the oligos or possible antisense that make homodimers or modify them in order to not dimerize. So because there was a risk, we say forget sulfur. And you know, I don't know if you follow the DMD field, but Prosensa GSK failed the trial with 2'-O-methyl PS. Wave, another American company, just failed a few months ago with the same kind of molecule, but claiming that they could do stereoisomers, and the problem was the stereoisomerization because of sulfur, make that there are two positions, and then there are some good, some bad, and they could identify the right combination, more expensive, of course, and they tried trial, and then it was again a failure because it was so toxic that they couldn't go up to 4 milligram per kg, which is homeopathic, and of course there is no evidence. So to avoid that, we say, okay, remove sulfur. Consider that our oligo should be sulfur-free. Because our tricyclo is sufficiently stable to not need sulfur. It's not regular DNA. And because we remove the sulfur, is used, you know, as a carrier, because it binds protein, and the proteins and the oligo will be delivered elsewhere, specifically or not specifically, who cares? It goes everywhere. So because we remove the sulfur, the oligo is like Teflon. Nothing binds, so you inject, the animal pays the oligo. So it's very expensive and no effect. Here, to avoid that, we decided to add a fatty acid. And the fatty acid will be taken in charge by the proteins that are involved in distribution of fat in the body. And indeed, this is again an experiment, proteomic experiment from Fedor. So here with beets, we attach the oligo with palm oil, with palm, of course, and with PO and also with PS. And here in that case is a full PO. You remember from the previous slide that it was Teflon, nothing bound to the sequence with PO, but in the presence of palmitoyl acid, this leash here, then you have some bands that are retained. Very few. It's not like previously. All the proteome here, it's very few. And they are mainly fatty acid transporters, carriers, natural. Apolipoproteins, serum albumin, and in some cases at very high concentration, which is crazy concentration, you may find something else, but this we are there at the level of the artifact. So we were very confident that this oligo would be very well tolerated. So here we are back to the compound for 51. We are lucky we have also a transgenic animal with a human gene. So there is no mutation. It's the normal human gene in the mouse. And we tested our compound, PAN, PO, Tricyclo. And we did 4 injections, 4 weeks at 200, just to be consistent with what. And here the results were spectacular. Just forget the biodistribution, it goes everywhere. Here the activity. You see, after 4 injections, we have 30% in the tibialis anterior, 60% in the gastrocnemius, about 40, and hurt, yes, about 20%. So these levels are therapeutic. If you have that levels in your tissues of skipping with something which is inflamed, you are asymptomatic. So we are very happy. The point is that 200 mg per kg is quite heavy for a man. You can do it in a mouse to go fast, but in a mouse would be more difficult. So, as we had problems before with a compound, full PS compound, which was found to be toxic, we say now if we have something that is promising, before launching a long-term experience and many animals and a long time, just check if it's compatible with the human blood. Because sometimes, in the normal course of the drug development, you test ex vivo on cells, then on mice, then on dogs or whatever, rats, then on monkeys, and then in man. And sometimes everything is okay until the very end, the compound is not compatible with man. So garbage, and you lose millions and you lose years, which is more expensive. So here we go just shortcut, take blood, human blood, fresh blood, and different patient volunteers, and we check if our compound activates some acute phenomenon that we know that will be detrimentous in vivo during the trials. In particular, the complement activation on the left and events on coagulation. So here you see the effect of PBS, phosphate buffer saline, the vehicle. So this is the background for the activation of the complement in human blood. Zimosan is a positive control, is a drug, a poison that activates strongly the complement, and you see the dark increase. And at 2 milligrams per kg, which is really very, very high dose, about 200 mg per kg, you see that the pan-PO tricyclo does not trigger the complement, while in presence of PS, you have an activation. And this is ex vivo. Not ex vivo, in vitro, using blood. For the clotting assay, it's the same. There are two tests, the PT and the activated partial thromboplastin time. There are two classical tests in the hospital. If it affects the coagulation, the time of coagulation is affected. And indeed, in the presence of sulfur, the gray one on the right here, you see that there is an anticoagulation effect of the sulfur, which could be tremendous. So imagine a trial, you start a trial, you activate the complement, you modify the coagulation, the authority says, stop, you will kill someone. Back to the trace. So we prefer to start our test, or all the study, with something that at least, we cannot test in human before the trial, but at least we check something, and we know that it's okay. So this was the first. Then, to make a long story short, I just moved to, I would say, the recent results using monkeys. So we are working now in a quite surrogate situation for humans. There are monkeys, so non-human primates. We inject in a similar way as in human. And the dose that we would like to use, 50 mg per kg. 50 mg per kg, we can produce that amount of compound. It seems to be not very toxic, or it's acceptable, and it has a strong effect. Because something which is safe but not effective is useless. Something which is very effective but that kills the patient is also useless. So we have to find the equilibrium, be very efficient and very safe. And very efficient in order, you will see after, to modify the regimen, not to inject every week, but maybe every month or every 2 months, just to alleviate the regimen for the patient, because it's quite difficult to come every week to get an injection at the hospital. After a couple of months, it's difficult. So in that experiment, here you have the compound, our compound, injected compound, and we did with different compounds, with sulfur and without sulfur. And we did some tests, classical tests, blood, cytokines, etc. Cytokines, this is for the acute reaction. And because sometimes the patient just are injected and feel very bad within the 24 hours after the injection, and you have to stop the trial. And after there is something different, which is a chronic effect, which is a poisoning. But the chronic is less dangerous because we can see it coming slowly, and we can stop it and reverse. But the acute can arise just in a minute after the injection, and you have to be ready. So here are the results. So this is the pharmacokinetics in the blood, and this is very important because in the presence of palmitoyl, you see that the compound stays, I would say, days in the bloodstream. Well, without palm, it disappears in 5 minutes. 5 minutes after the injection, there is nothing in the blood, nothing that you could detect. Kidney is full, liver is full, urine is full, tissue there is some, but there is nothing in the blood anymore. Here, 10 hours, well, not in minutes, but in hours, you have still half of the compound that is circulating with the palm intact, running, and this may be explained why the compound is better transported. I have almost finished here. What about the complement activation? We saw that before it was okay in human blood, but here is in vivo situation after different injections. So PBS, SARS, 0, nothing happens. So we have 3 markers for the complement, not only 1. Our compound with PO is flat also, so no difference with PBS, so there is no activation. While the same sequence with the sulfur, you have a huge increase of complement. So the monkey is fine, but there is a complement activation. Complement activation, the regulatory authority says stop the trial, too dangerous. So even if the animal feels good. What about cytokines? Because complement is only one aspect. Cytokines, and then you can have a shock, an anaphylactic shock. So here we use a control that do the job, positive control, which is a similar guy with a full PS and injected very fast. In that condition, you just trigger cytokine. So you see that our compounds do not trigger significantly with an injection time of 30 minutes. But here, advantageously, the CRP, which is produced by the liver, is not produced at all with the compound PO, while it is with the RAG-PS. So again, PS is bad, PO is fine, and PO seems to be very well tolerated, and coagulation is not affected, while with the PS it is, like human. And here is activity. This is the most important, and this is really spectacular. Here you have 2 monkeys, so it's duplicate, treated with 4 injections at 50, and we sacrifice the animal after 1 month, and we check for the level of skipping. And here you have the parental band, meaning the band, the RNA that has not been spliced, which is present in the muscle or in the tissues. And here is the amplicon that mark the skip mRNA, delta 51 in that case. You see that in all muscles there is skipping, in all animals. The most impressive is heart. The parental band has almost disappeared. It is not quantitative, but it gives, when it's 100%, it's 100%. I mean, what to quantify? In the 2 animals, the heart is pretty well. And here, in the muscles, in the tissues, after only 4 injections, it's at least 30 and more, but let's say 30% to be pessimistic. But we know that it's more after only 4 injections. And of course, this treatment is for life. And after 8 injections, the activity would be higher, and 12 injections higher. We don't want to treat it as a continuum. Here you have, this is with a surrogate, but we have the same with this kind of compound, not yet in the monkey, but in the mouse. And here you have the level of compound in tissues. This is arbitrary unit, so consider the quanta of tissue of compound. So with the clearance, the weekly clearance and injection. So you have in orange 4 injections, in blue 12 injections, and then wash out. And the dots are the activity in percentage of skip with a surrogate. So you see that the activity increase with time and number of injections. It is not multiplied by 3. Here it's 4 weeks, 12 weeks. So we do expect 3 times more activity, but it is not 3 times. It's 2 point something. And then wash out, so no treatment. And then we lost about 3% activity per week, which is nothing. We lose a third after 3 months. So meaning that the activity is very stable over time. So the treatment lasts. It's a lasting treatment. And the compound disappear. So this allows us to propose a specific regimen, not to treat forever, but to have here a bolus of treatment, 4 weeks, then 4 weeks remain at home, stay calm, the compound disappear from the liver, from the kidney, etc., from the tissues in general, and then again, a treatment of 1 month, etc. So this alleviates the regimen. Could be 2 weeks, 2 weeks, but this is the proposal. And the agencies apparently like that kind of protocol. And because this is personalized medicine, because you have to consider the pattern of deletion of the mutation, so it's quite personal, even if there are groups. We know from the animals, and this is a rule. I mean, we're not equal in front of drugs. Some are more sensitive than others. So it's meaningless to make cohorts and to go, with a cohort of 4 patients at low dose. If it goes well, we take 4 patients and we increase dose. It's personalized, like for cancer. So each patient should have his individual maximal dose. So we have to find that. So we consider that all patients here are 8 ambulant patients and 4 non-ambulant and wheelchair. We start at 5 mg per kg, which is very low. We do not expect benefit. We do not expect it should be safe, but we have to start at very low. And then if everything goes well, complement, coagulation, platelets, cytokines, and biomarkers, next week we go to 10, then to 20, 30, until 50. We guess that 50 is still safe for everybody, but we have to go progressively. And then some patients can maybe stop at 40, just because at 50 is not good, but 40 was good. And then we can stratify into cohorts a posteriori and not a priori. And then we start for 4 weeks trial. This is this period, and then stop. Of course, at each injection, we will check for all these markers, not for activity, but in life observation, headache, fever, etc. And after a period of time, likely 3 months or 6 months or 1 year, we don't know yet, this is in the discussion, we will do muscle biopsy for all patients and check for muscle function, particularly for those that can walk, because 6-minute walk for a wheelchair, it could be easy. and of course, safety issue. And if everything goes well, we maintain all these patients under the compound at our cost. We don't ask for reimbursement, and then we'll move to other diseases. So just to finish, but I think I talk about that more or less during the talks of the self and something I didn't say is that these oligos also go into the CNS, and we can rescue some cognitive defects in the mouse. Not all, but we don't know how to measure all the cognitive defects in Duchenne, in the MDX mouse. But the fear response is completely restored. I mean, there are many things that are restored. Of course, the cardiac function is fully restored. The respiration is also fully restored. The resistance to eccentric concentration is restored. So everything seems to be restored with a surrogate. With a 51, we don't know yet because we have not a proper or correct animal model for that. And even if we had, I mean, the answer should be done in man and not in animals, because who cares if it works in mouse and not in human? This is meaningless. And last but not least, our group, not everybody was there, but it was pictured, it was taken last year in Monaco. So there are people from Bern, from Paris, from Sky, from Sintena, and from the unit. And here you can recognize Fedor here. He was here, and the Prince Albert will support us. It's very important because it's a small country, Monaco, but he has a seat at the ONU. I mean, UNO. He has a seat at the UNO Secretariat of the World, so it's useful for us. Thank you very much for your attention, and I'm sure that I am on time.
Так, вопрос, пожалуйста. Okay, let's understand. So what do you think about other diseases? So it look like a very efficient tool, very efficient drug. What do you think about the next targets?
Next target, so in Duchenne there are 79 exons, so this is for exon 51. So there are other exons, 45, 53, 16. I mean, there are plenty of work on Duchenne only.
Just on Duchenne.
Yeah. But this kind of approach we're developing also on SMA and Pompe disease and Steinert, for example. And something which is very important is that here we do exon skipping. For SMA and Pompe, it's not exon skipping, it's exon inclusion. Because the mutation, the natural mutation, in the case of SMA, it's a fantastic story. All of us, we have 2 copies of SMA. It encodes the protein, a SNP, something which is involved in the biogenesis of SNPs. And if we have 1 copy, it's fine. We are safe. If we have the 2 copies mutated, I would say in real life, I mean, in the mammalian kingdom, you die. I mean, you don't die, you don't live. There is abortion, early abortion, and at the embryogenic. But in human, we have something peculiar, in similarity, maybe it's one of the things that make that we're human, that this part of the chromosome was in the past duplicated. And we have multiple copies of something that was called at the very beginning a pseudo gene, SMN, called SMN2. So we have multiple copies, and but different numbers, each of us. Maybe, I don't know how many I have. Yeah. Maybe I have 4, maybe you have 8, maybe 0. But if my 2 copies of SMA are fine, I don't need them. But these copies, multiple copies, are pseudogenes, meaning that they are not supposed to work. They have a mutation, what we call isosemantic mutation, meaning that in exon 6, in exon 7, of course, is amino 6, base number 6. The 6 base of the exon 7 change, and it doesn't change the amino acid. Okay, so apparently this mutation shouldn't have effect, but it has an effect on the splicing because it turns a splice enhancer into a splice silencer, and then the exon 6 is not included, 7 is not included anymore, and the protein cannot be produced correctly. Fortunately, there is an ISS, intronic splice silencer, downstream of exon 7. And this silencer is very strong in the normal situation, genes. But if you design an antisense that masks this silencer, you wake up the splicing of SMN2. So in this patient with SMA, they cannot produce SMN protein from their 2 mutated alleles, but we can rescue the protein from their pseudogenes by awaken the copies. And for Pompe, something similar. Pompe has the very structure in its exon 2, which is excluded from the messenger, and exon 2 contain the ATG, the start codon, and it's because of there is a specific folding of the messenger that make that with a common mutation which concern about more than 50% of the Caucasian patients and more than 80% of the survivors. This mutation makes that the messenger make an hairpin, and by making that hairpin, it masks the splice site. So it's the same with an appropriate antisense that unfold that hairpin. You just deliver all the mechanisms, all the sites that are involved in the cathedral of the splicing, and the splicing is normal.
That's amazing. But just in general, we know, I mean, after all the sequences of the different genes for the human disease, can you just estimate
the majority
is not sequence?
It's not. Is splice mutations.
So you mean that your approach can be applied for what? For majority of human diseases?
Many.
Really? Well, that's the problem.
Fabry, for example. But look at Fabry. Fabry is fantastic. Fabry there are many mutations in Fabry. Okay, and it's a very rare disease. I think it's one patient Out of one no, but look,
yeah, okay,
you'll
okay.
see. I think it's 100,000 incidents, except it in China, Japan, and Korea. I mean, in Eastern Asia, where there is a common mutation because there is a founder, and then is 80% of the population with a disease has the same mutation, and it's a SPLICE mutation.
Yeah, but that's another problem. You can apply this approach only for the proteins which are required in your everyday life. You cannot treat with this approach, I mean, developmental diseases, which, like, it's activated somewhere in embryogenesis, and that's it. You cannot cure it.
No, you can, but there is an ethical problem. It depends if it affects the mother or not. Because I mean the embryos in mammalians are in the belly of the mother, so these compounds can cross, or we can make them cross.
Did
the
you
placenta.
try it? Go.
Some with some modification we found some, but it's not massive. But we can improve that. The point is that if you want to accede to the fetus, you have to go through the mother, and maybe the compound can be tremendous for the mother. So it's an ethical point of view. Do you sacrifice the mother to the fetus?
That's another question. How many cases off target? Because you plan this.
Three cases off target. Three cases. The first is exon skipping. Or the mutation that depend on the structure, the very structure of the protein. The protein should be compatible with that.
Yes.
Then there is exon mutation. It includes all splice mutation that are leaky, because these are leaky means that you can rescue, and whatever. And then you can kill a protein, a dominant protein, because the same way that you can rescue a reading frame, you can also abort a reading frame. For example, if you remove exon 51, you or me, we become Duchenne. A Duchenne with the right pattern of deletion, you restore a reading frame and you turn Duchenne into Becker. But I would say wild type, normal individual with normal dystrophin, the same treatment will kill his dystrophin and turn him into DMD. Becker first and then DMD. So you have also all these approaches for cancer, for example. If you need to kill, it's kind of RNA interference, but you don't need RNA interference. I mean, you can use, for example, gapmers and things like that. The problem with gapmer is that once you stick somewhere, it cuts. So all the off targets will be killed too. So there is a lot of side effects. It's a victory, purist victory. In the case of exon skipping, to remove an exon and kill a messenger and then a protein, we don't want that protein at that level, it is not so efficient. And annealing is not enough to have an effect. You have to anneal in the right site at the right moment. If you are just few nucleotides out of the right, it doesn't work. You stick, but no effect. So this reduces a lot the number of off targets. So it's maybe more clever to use exon skipping to kill a messenger by killing the reading frame rather than using something which is very efficient, but with a lot of side effects, potential side effects.
Questions?
Louis, please, can you tell us a few words about the metabolism of the palm tcDNA compound?
Oh, the palm. This is one of the reasons we decided also to utilize fatty acid. For example, in the body, I will come after for the fate of these molecules, how it is degraded, where and how. But first, why fatty acid is important to target a kind of compound to muscle, and it is likely that it will work better in man than in mouse and monkey. We have two types, to make it simple, of muscle fibers. Muscle fibers that are involved in sprinting, so very fast. They are anaerobic, they use glucose, and there is the slow type muscle fibers that are involved in marathon, if you want, like heart, never stop, diaphragm, never stop. So these muscles use oxygen and they burn fat. And it is like that, but man is more a marathonian than a sprinter. So we have a lot of slow type fibers. So they would prefer fat than sugar. So these oligos coupled, conjugated to fatty acid would be better incorporated into human muscle than in models. So it works well in animal models, but we guess it will be better in human. Now, what is the fate of the compound? The compound is quite stable in the bloodstream. In the bloodstream, we see only the full compound, fatty acid, linker, and the oligo. Once it's in tissues, the fatty acid is not found, excepted some extra cases, exceptional, and we don't know if it's a mistake or a contamination of the machine, etc. But in the vast majority of cases, we do not find the palmitoyl in the tissue, only the part of the antisense itself with a linker. Because we add a sulfur, there is only a single sulfur between the linker and the oligo to reinforce, to secure the carrier during the trafficking in the bloodstream. If there is no, if you miss that sulfur, it is cleaved in the bloodstream because it's phosphodiesterase will kill it. And then the compound is slowly degraded. We don't know exactly where. It's likely that it is degraded in lysosomes. And when this is why I did not give too much emphasis to the biodistribution. When you look at the biodistribution, you take the whole tissue. You don't know where it is. It is in endosomes, outside the cell, inside the cell, in the nucleus, in lysosomes, in the cytoplasma. You don't know. You say there is. And it's important to know that there is. And this amount will decrease. What is to have to keep in mind is that the oligo that does the job is exon skipping, is the oligo which is in the nucleus. Splicing occurs in the nucleus, not in the cytoplasma. So if the oligo cannot reach the nucleus, there is no skipping. If it reaches the nucleus efficiently, there is work. And then the decrease we see over time, per week, should be much more complicated because depending on which compartment is the oligo. In lysosomes, it will decrease fast. Endosomes, depending what type. In the nucleus, maybe it stays for a while, but there is very few. This is why the activity stays for a long time, while we do not detect so much oligo. It's the very few that are in the right place, and that stay longer. So it's well, okay. And the price, the cost to reach that level is to inject 50 mg per kg. It's brutal. Vast majority goes where you don't know what, you are not interested, but there is enough in the right compartment to give a benefit. And this is what we look for. Of course, if we can improve the nuclear import, it would be better. We need less compound, less toxicity, and long-lasting efficacy.
Okay.
Excuse me, what is the cost of this oligonucleotide derivatives?
So far, it's not for sale. So the cost is cost for research. It's like a prototype. So far, yeah, we spend millions per year to develop that. But it's development. It's not the cost of the oligo. The oligo is not so costly at the end. When it is done, it's phosphoramidate. It's the same. To produce the oligo is the same as to produce DNA or RNA or whatever. With the same machines. The cost is the building block. To make the building blocks. And this is today expensive, as likely the first smartphone was very expensive, but now it's not expensive. And I think this is the same.
Can you just estimate?
Today, if you want, no.
The cost of treatment.
Treatment, it would depend on our appetite for money. Because, I tell you just a story. Deflazacort, you know what is Deflazacort? You know how much it costs? My stepson is Duchenne. He's 28. And he take a pill of, it's corticoid, pill of Deflazacort. It's not available in France. So I go to the border, Spanish border, and then I buy the compound, 1 pill per day, for 1 year. It costs 250 euros for 1 year. Less than the coffee. You know, the Nespresso is more expensive. The morning takes one, it's more expensive. So 300, let's say for 300 euros per year, less than one per day. There was a company in America, it was 5 years ago, they decided, because it was not allowed, this compound in States, but it was in Canada since many years as well, in Netherlands. So they decided of a trial phase 3 trial. And it was not successful because it's not a miracle, but it was a benefit, a little benefit. Then the FDA gives the authorization to market the compound. It is completely generic, okay? It is made by hundreds. Give a price. $89,000 per year. Okay, so the cost of a drug, I mean, there is a cost and the sale price is different. The cost is nothing. The sale price is, so this is the same. Today, if you want to start from ground zero and repeat that, you need at least 4 million per year for 5 years. This is to start from ground zero. It's like making a car from nothing. But now that we have the routines, we have the facilities, etc., it costs less and less and less, and one day it would be very cheap, and likely that it would be a regular compound. It would be a regular compound. But today it's expensive. And if investors take that, it would be $1 million or $500,000. If we have, for example, just to have in mind that something that doesn't work is sell $500,000 per year. Okay, imagine that something that works.
What's this famous French made of the duck, of Iberian duck? That's
Iberian duck?
to cure oxycyclo, something like this. You don't know?
No?
That's very popular drug in Russia.
Yeah.
It produced by French firm. It called oxycyclinum, something like this. It made of the liver of Iberian duck.
Really?
Yeah, and it's very good against flu because it's potentiated and diluted in, up to 1 molecule per universe, and it cost in Russian market it cost 600 rubles, which means roughly 10 euro for the course. Yeah.
Yeah.
Well,
but there's nothing inside.
Very efficient. Very efficient. Homeopathic. Okay, any more questions?
No, but just to answer seriously to your question, what we want, because, behind us are charities, are patients, and the idea is not to make money with that, abusive money. But what we want is to make it available. So far, it is not for sale just because, these guys, we receive money from charities that organize a donation. So the donors, in their mind, they are paying for the compound. They are not paying for us to play. They are paying for the compound. So we consider that the compound is already paid. So we'll offer it. So we are not looking for a marketing, abusive marketing. We want just to allow the system to last. I mean, we need money, of course, to pay people, to promote new projects, new diseases, etc., but not to make abusive benefits, but should equilibrate the cost. So far, we do not, and it's fine because there are donors, and I think there are other business models. There are billionaires in this. Okay, there are people for who million is nothing. Really, million is nothing. There are people like that. So just you can say to that people, and there are millions of that, adopt a patient, pay for him.
Okay, more questions? No. Thank you very much, Luis. It was a wonderful lecture. Thank you. Usually put the presentation and the video on the web.
You can use the video.
But not presentation.
No, because there are some things that are.
Okay, it's all.
I don't want to.
But video is.